Good morning. Lingying, thank you for that introduction. Today I want to talk about energy hierarchy and building design. I think we're all here because we're interested in environmental friendly design, passive design, energy efficiency measures, but it's often hard to know how you implement things, how you make decisions, what's important. There are a number of things out there that you can use as guidelines. They could be building codes. They could be some of the systems that Victoria has just talked about, whether it's LEED, Passive House, Min Energy. Am I doing all right here? Okay. Or they can be any number of sustainable bits of technology that we can tack on to whatever houses or automobiles we use. But basically, it's a little bit difficult to see the forest for the trees in terms of what are the opportunities, how do you take advantage of them in a way that recognizes that certain decisions perhaps make more sense than others. So what I want to do today is make a simple analogy between something that we already know about waste hierarchy, reduce, reuse, recycle, and an idea of an energy hierarchy. The effectiveness of reduce, reuse, recycle, apart from the alliterative quality, is that it's very easy to implement. You know, first of all, you want to reduce the amount of things that you consume. After that, you want to reuse items when possible. And then lastly, you want to recycle things before they're thrown away. There's a similar hierarchy for energy, particularly when talking about residential construction of conserve. That should be control and convert. Sorry, there was a little issue converting from PDF to PowerPoint this morning. Shares a similar property with reduce, reuse, recycle in that you start at the lower bit of the triangle where decisions have the greatest impact for the least cost, and you move up. Conservation strategies are about preventing unnecessary energy use, largely through passive means. They're also about behavioral strategies, which are a more complicated sort of issue. A tier up from there is control, being sure that the energy that you are using, you're using as effectively as you can. And then at the very top is convert, basically making energy from renewable sources. What I want to do briefly this morning is make a brief description of these three tiers and then talk about how you can use them in this order to maximize the effectiveness of your energy decisions. So starting with conserve or conservation, largely about passive building and behavioral strategies. It's going to have the largest impact with the least expense. It's going to happen in a pre-schematic or schematic design phase, which I'll explain to you in a moment, and it's also going to be around building occupant awareness and education. I should say that green homes are great if you're going to build a new one on an empty site, but a lot of us live in apartments or live in older homes or live in contexts that do not allow all of the advanced technology to be used. I think that this hierarchy, conserve, control, convert, will work for anywhere you live, any residential type of context, maybe not renting as much as owning, but generally is very flexible. Just a bit of vocabulary. Passive climate control systems don't rely on you buying any energy and typically rely on using bits of the building that already exist. So for example, sun shading is an example of passive climate control technology. It's a little bit unfortunate it's called passive because it is not at all passive. It's actually quite actively engaging with what is the building, its envelope, and its interior. The opposite of that would be an active climate control system, basically where you have dedicated equipment that runs off of energy. So the first tier, convert, largely relies on passive climate control. A word also about project phasing and why it's important to have a sense of hierarchy and when you begin a project so that you can set your priorities. In a typical construction project, it goes through a number of phases that might start with research or setting of goals through what would be schematic design, design development, construction documents, and construction. And there's an inverse proportion to the opportunity for influence and the cost of making changes as you move through a project. So the earlier in your project, you're able to set priorities, understand hierarchies, and implement them in terms of a decision-making process, the least it's going to cost in terms of making changes later. As you go down this path, as more and more decisions are made, it becomes more and more expensive and more difficult to change your mind. So it's very important to have the priorities set at the beginning of a project, particularly at the conservation level. First point would simply be that context matters. Where you choose to build has a direct impact on how people get there. And as much as we like to talk about buildings, a huge portion of the energy used related to buildings is people getting there and getting somewhere else. So the more that you can rely on public transportation, walking, cycling, the less impact that building is going to have. The more you can tie into existing infrastructural networks, the less need there will be to expand service grids. Again, this is not a choice all of us can make, but it's important to realize in terms of a conservation strategy, it's a very significant one. Another choice is building new versus building or renovating an existing structure. The cliche is the greenest building is the one that you already have, not the one that you need to build. And in fact, the USGBC, along with the National Trust for Historic Preservation, has done a study looking at various building types in various climates of the United States, and basically found that renovating existing buildings in almost all project type is a more energy efficient decision than tearing down an existing building and building a new, higher performing building. So yes, you can build a green home even if you already have the home. Second sort or third sort of moving down, that climate exists at many scales. May be familiar with the idea of a macroclimate, the climate that exists at a sort of international scale. But those types of decisions equally apply to a microclimate, to the scale of a specific site. So this is a drawing basically showing that climates exist on a hill, which just happens to be in Ohio, in the same way that climates may exist over a much larger geographic region, largely having to do with sun exposure. Again, all of us don't have big sites where we can choose to put a house different places on the site, but where it exists in the site in terms of solar access is a significant conservation decision. And then even at a smaller scale microclimate site, looking at the landscape of the site in terms of deciduous trees being able to block sun in the summer, allow sun through in the winter, or looking at more specific landform or building form in terms of blocking or encouraging winds. All of these things can be relatively simply tested with software if you hire an architect, or maybe you're an adventurous homeowner and can figure it out on your own. But it's very easy to make these decisions, to do these simple tests. As we move down further, controlling the building's massing. Massing is just a way of saying shape. Of course, many things influence the shape of a building. We need an orientation toward a road. We want a view toward a certain perspective. We want windows in one direction or another direction, but considering how the sun moves around the site and considering what the landform is or what the topography is around the site has a significant impact on how much of that facade is exposed to sun, how much of it is blocked from sun. So a lot of this research is actually nothing new. We're going to hear a lot about cutting edge technology. Most of these issues about siting and massing have been around for a long time, and these images are in fact from a book from the 1960s where they sort of take the square plan of a building in a summer condition and a winter condition and show by simply tweaking the form and adjusting the landscape, they're able to minimize heat loss and maximize heat gain in winter and minimize heat gain in summer. Understanding your building's thermal envelope. Victoria touched on this a little bit. Thermal envelope is just a fancy way of saying how well your building is dressed. We in Ohio have the benefit, if you like, having spring, summer, winter, fall, of having 4 seasons. But it also means that it's very cold outside in the winter and it's very hot in the summer. And if you think personally how you adjust to these climates, you change your clothes. You wear something different in the summer than in the winter. Houses obviously can't do that. We need to design buildings for one season, but have them perform in many seasons. We want to look at basically 2 types, the transparent part of the building and the opaque part of the building, and look at some simple metrics for each. For glass is, we tend to think of it as nothing, but it's actually a very sophisticated material. We want to be able to allow in light, but typically block heat. And since they both exist along the electromagnetic spectrum, it's a very difficult thing to do. We have something called an solar heat gain coefficient, SHGC. It's a very important way to judge the performance of your window. Also have a U value for window, which is the insulating value of the window, which is really just the inverse of the R value, which is the insulating value of the wall. And then also understanding the air tightness of the wall. Again, this is great for new construction. Victoria mentioned blower door tests. As part of an existing home, you can have an energy audit, where they basically will come in and through a battery of tests, the primary of which are a blower door test and then some thermal imaging, understand the type of thermal envelope you have as an existing building and then give you some simple ideas about how to improve that. And then finally, behavioral changes. This is, in a way, probably the most difficult category in many public buildings, because we have lots of people with lots of different needs doing lots of different things. It's probably the easiest in the home because you're the one that makes the decisions. It's not necessarily about building physics or technology, but it's about sort of social and cultural preferences and expectations. Do we expect it to be the same temperature inside all year round? Do we expect every room to have the same temperature? Or can we change our behavior by, as Jimmy Carter suggested in the 70s, putting on a sweater? Or do we want to have an idea where we want to heat the person and not the room? This is a much more complicated type of issue, but it has a significant impact on how energy is used, particularly in residential settings. So moving up the triangle to the next tier of control, and I will say they'll get shorter as I get further up here. This is one that looks at mechanical and electrical equipment. It allows for reduced energy consumption without necessarily changing the conditions on the inside. It's for new construction and retrofits. So here, we're dealing mostly with active climate control systems. We're familiar with this sort of energy fuel economy guides, probably most likely from when you buy a car. You look on the window, they have a sticker, it tells you pretty much what you expect your mileage to be for city driving and for country driving. There are countries where they have what's called a building energy rating, which is basically the same thing as this sticker, but for a house. It looks at space heating, water heating, ventilation, lighting for the entire house and gives it a rating from, I can't read what it is up here, but up to an A. This is a very effective system for a couple of reasons. One, because it lets a potential homeowner consider operating costs as well as first costs. And also because then banks and institutions that provide financing can consider these decisions when deciding whether or not to give a loan. So instead of the amenities of a house being, stainless steel appliances and granite countertops, you can say this house has an A energy rating, meaning that it's not going to cost you very much to operate. We don't have a system like this in the US. We have sort of equipment level stickers or equipment level ratings. Primary among them are going to be the AFUE number, which is annual fuel utilization efficiency, basically for anything that burns fuel, natural gas, as an example. Tells you where it stands on a scale from least efficient to most efficient, mostly going to be for heating equipment, furnaces, water heaters. A SEER rating, so seasonal energy efficiency rating, is going to be for air conditioners. How much cooling do you get out for each kilowatt of energy that you put in? And then more generally, an Energy Star rating for domestic appliances. These are all important things to look at. It's up basically to the homeowner or to the contractor to do the math to understand what's the best decision for each category. It's a little easier with lighting. With lighting, we look at a number called efficacy, which is how much energy do you put in versus how many lumens of light do you get out. It's a pretty linear story in terms of moving from incandescent, which is more efficient as a heater than it is as a light source, through compact fluorescent to today's LED fixtures. You can kind of see how the efficacy has increased from maybe 40 to 70, let's call it, for compact fluorescent, up to close to 200 lumens per watt for LED. It's a very simple fix for improving the lighting efficiency in your home. And then finally, building controls. Again, not something we think about too much, Victoria mentioned the issues of set points or setbacks, certainly something to consider, but these can be quite simple. They can be occupancy sensors that go on when someone comes into the room, goes off when they leave. They can be timers that you might have on a bathroom fan or on an outdoor light. They can be something much more complicated, for example, the Nest, which has made a great impact in residential design in the last maybe 5 years. In terms of a cyber-physical system, a system that ties into your phone but also ties into your furnace and understands your use pattern. Just one more point, or two more points before leaving the second tier of control. One is that energy codes work. This is a chart put together by Arup, a sort of international engineering firm looking at energy use in California versus the rest of the United States. California had very strict energy codes, starting with the energy crisis in the 70s. You see heavier line is US, lighter line is California, increasing energy use. California plateaus in the 70s when they institute energy saving regulation. American general energy use continues to go up. Energy codes work. Second point is the sort of limits of efficiency in terms of achieving goals. This is a chart by ASHRAE, basically the Society of Heating and Refrigerating Engineers in the United States, looking at the amount that different technologies have reduced in terms of their energy usage. So looking at heating, looking at lighting, looking at cooling, looking at the envelope, and then comparing the slope of those lines to the net zero 2030 challenge goal. Basically, the slope of these lines are not going to meet the slope of those lines. So energy efficiency itself is not going to be enough. So the 2 points here is that energy codes work, but energy efficiency itself is not enough. The last tier, convert, basically relies on renewables. This can be PV or solar thermal. It can also be energy credits. In a certain sense, this is the most exciting category because we have a lot of solar energy. If you simply just compare the anticipated reserves of all finite fuel sources and even the potential of all renewable sources to the amount of solar energy that is available, solar energy is by far the largest category. I'm not going to go into this in any detail because we'll hear a lot more about it this afternoon, but basically the two technologies, solar thermal, making hot water, or PV or photovoltaic, making direct current. Okay. So in conclusion, setting priorities for energy doesn't have to be difficult. It can be as easy as the reduce, reuse, recycle that we hear every week in terms of conserve, control, and convert. The important thing is to understand what category the different types of decisions you're considering fall into, and then acting on those decisions in a hierarchical way, basically to get the most out of what you're putting in. Thank you.